All right, good morning. Okay, so today I am going to talk about the last two sections of chapter 3. So 3.6 is reactants and products. And then 3.7 is limiting reactants. Okay. And there's a certain amount of material in this section, in these two sections. So you can certainly watch this video as well. There's also the video I did last semester. So if you look in my videos on YouTube and look for spring 2021, you'll see that actually I covered it twice because I covered it for two different courses. So it's in there as well. So there's a lot of videos if you want to watch them. Okay, so let's go ahead. I'm going to just sort of work on Alex's problems here. So the first one that I want to take a look at is using a chemical equation to find the moles of the product from the moles of the reactant. So you're using the chemical equation. So you have to write the chemical equation and balance it in order to do this problem. So we're going to use the chemical equation to go from moles of the reactant to moles of product. Okay, so let's take a look at it. So in this particular example, they're talking about gasoline. There's a compound in gasoline which is called octane. And octane is, they give you the chemical formula. Okay, so there's your chemical formula. And what they do is you burn it in air. Okay, so that's how an automobile engine works. You burn it in air, and what they tell you is to react it with oxygen. So that's O2. When it burns, when the octane burns in oxygen, you produce carbon dioxide. So carbon dioxide, carbon, C, dioxide, di means two, so two oxygens, so dioxide, and water vapor. So here's your water. So they tell you the states of matter. They tell you the octane is a liquid. They, of course, air is gas, right? So oxygen is a gas. They tell you it's carbon dioxide gas. And then they say vapor for water. Vapor is just another way of saying gas. It's just a term that we use for water. Okay. So it says here that if you have 0.085 moles of oxygen. Okay, so that's given. So notice what I did. I wrote it right underneath the oxygen. Okay. Let me come over here. Hold on 1 second. So I wrote it right underneath the oxygen because that's the given information right there. They then say, calculate the moles of carbon dioxide that will be produced. So how many moles? Remember, the abbreviation for moles is MOL. We just covered that on on Wednesday. So how many moles of CO2 are there? So when you're doing these types of problems that involve the amounts of material, make sure you balance the chemical equation. So that's our first step, is to balance the chemical equation. There are 8 carbons on the left side. So let's put an 8 on the right. Okay. So carbon is now balanced, right? 8 and 8. Next, let's do the hydrogen. Now, why am I doing it in this order? If you recall, earlier in the week, what I said was when you have these sorts of equations, the element that's all by itself, if there is one, and in this case there is oxygen, the element that's all by itself, you do it last. Do the other elements first. So I did the carbon, and next I would do the hydrogen. 18 hydrogens. The idea is that there's some number in front of the water, I'll call it N, that we can put so that that number times 2 is going to equal the number that we have on the left side. So really, you're just doing basic algebra, right? Really what you're doing is you're saying 18, which is on the left side, is equal to some number N times the subscript, which is a 2. Okay, they have to be equal to each other. So you divide both sides by 2. And that gives you N. Well, 18 over 2 is just 9, right? So now you have 9. Okay. Now, I didn't really show it being done that way, but we actually did the same thing for carbon. For carbon, what we had was 8 on the left side. And then again, you could say, look, there's going to be some number here that times 1 though, right? Because there's a 1 there, even though it's not drawn in explicitly. We don't draw in 1s in chemistry. Even though we don't draw it in, there's a 1 there. So what happens? Well, you divide both sides by 1, and then just N is equal to 8. So that's why that worked out. That's why I didn't show the algebra there. You really are doing the algebra. I just didn't show it. So now we're almost there. We've got the carbon, we've got the hydrogen. Now we got to do the oxygen. Now, here's the thing. See how I didn't do this one until last? Now we know why. Because now we can change that number there and not affect any of the other elements. If we'd done oxygen first, then carbon, and then hydrogen, what would have happened is you would have balanced the oxygen, and then you would have tried to balance the carbon, and the carbon would have affected the oxygen. And so it's a problem to do it that way. So you just want to find the element that's all by itself, if there is one. Sometimes there's not. Okay, so same idea, equation. There's a 2 subscript, so N times 2 is on the left side. Think of the arrow as like an equal sign. That way you can treat it algebraically. So N times 2 has got to equal what's on the right side. So 8 times 2 plus 9 times 1, right? There's only 1 oxygen in the chemical formula of water, okay? So what you get is 2N, right? N times 2 is 2N. 16 plus 9 is 25. Divide both sides by 2, and you get 25 halves, okay? So that's actually a pretty useful way to balance equations. It's certainly not the only way, but it's pretty useful for this. And then what you can do is, if you want to, you can say, look, we don't want fractions, so we're going to multiply both sides by 2, okay, to get rid of that fraction, right? Because 25 halves times 2 is 25, and that'll give you whole numbers. Generally, you want whole numbers. So 2 of these. Two times 25 halves is 25. 2 times 8 is 16. And then 2 times 9 is 18. So it's still balanced. It's actually balanced. It's just the only thing here is that everything's is a whole number. That the coefficients are all whole numbers. That's all we did with that last step. Many people will actually leave it in this form. You just have to be careful. If you're doing a problem where the computer software is asking you to balance, they're typically going to want whole numbers. They'll tell you. They'll say, look, balance it with whole numbers. If that's the case, then we would do this. There's nothing wrong with this equation with having a fraction in it. That's perfectly fine. But most software programmers try to get you to this point. Okay. So now we've got the balanced equation. Now you do the math. Now here's essentially the idea. Those coefficients are telling you the ratios of everything in the reaction. So this is where you get all these sort of analogies, right? Like sandwiches or cakes or factories and things like that. What this is telling you is that 2 of these particles is reacting with 25 of those. It's a ratio. So it could be 2 to 25. It could be 4 to 50, right? What did I do here? 2 to 25 is a ratio. That ratio is the same as 4 to 50, right? I just doubled both of those numbers. Or 20 to 250. Here I took this one and multiplied it by 10. That's the idea of a ratio, right? Like if you have 50 dogs, the ratio of legs to heads is 4 to 1. There's 4 legs for every head, or 4 legs for every tail, okay? If you have 50 dogs, the ratio is still the same, right? It's still going to be 4 to 1. It's just that you have more of them. Let me admit both of these people, okay? Sorry. So the same is true here. This 2 to 25 ratio can be scaled up to any number. And that's what this problem is really getting at. It's saying, suppose we have this many moles, 0.085. Let me write it over here. How many moles do we have here? Okay, the key here are these ratios. The ratio is 16 moles of carbon dioxide for every 25 moles of O2. And that's really what you want to do. Let me erase all of this.
Wait, Professor, can I take a screenshot?
Okay. So in the question, they're asking us for the moles of CO2. That's the question. We're given the moles of O2. This is given. So here's how you go about it. You take the moles of the one that you're given, which is 0.085 moles. I'm actually going to explicitly write in the chemical formula just so that you see it. To find the number of moles of CO2, we just multiply it by this ratio, CO2 to O2. It's 16 moles of CO2 for every 25 moles of O2. Okay. Now, I wrote it this way to show you the dimensional analysis. Moles of O2 cancel, and you're left with moles of CO2. So now it's just doing the arithmetic. 0.085 times 16 over 25. And you get a small number. You get 0.0544. Now, that probably has more significant figures than Alex would accept. They would probably say round it to 2. So this would be the most significant. This would be the next significant. So 0.054 would be your answer, right? That's 2 significant figures, or 2 significant digits, if you want to use that terminology. All right. So the ratio is, just like I said, if you look at a dog, you've got four legs for every tail, right? So the idea would be four times. So if I said, hey, I've got these number of dogs, and I've got, 50 tails. And then you said, okay, I got 50 tails. How many legs? What you do is you take the given piece of information, which is 50 tails, and then you would just multiply that by 4 legs per tail, right? That's the ratio. That's what the balanced equation is telling you. It's just telling you the ratio of one to the other. So now you get 200 legs. And that makes sense, right? If you have 50 tails, that means you have 50 dogs, which means you have 4 times as many legs, right? So it's that's essentially the same idea. This number, you could write this as just like 2a plus 25b goes to 16c plus 18d if you wanted to use just a symbol. And that gets away from the chemical formulas. The only reason we need the chemical formulas is because we're doing chemistry. But that's essentially the idea behind this whole thing. So if I said, look, I've got 0.085a, and I wanted to find C, I would just multiply that by 16C for every 2A. And then you just have, 16 halves is 8. So you'd be multiplying it by 8. Okay? Very simple. That's if it's in moles. The only thing that you have to be careful with is that when you do the problems where they give you the mass, they give you the number of grams or milligrams or micrograms or kilograms, you can't do that step that I just did there till you convert them to moles. Because the idea behind this problem is that you're counting things. So there's 2 moles of A, 25 moles of B. If it's in grams, that's a mass. That's not counting. When I say that there's, when I say that a cake weighs 2 pounds, that doesn't mean there's 2 cakes, right? That means it weighs 2 pounds. So to find out how many cakes you have to know how much they weigh, right? You have to know that, oh, each cake is 1 pound. So if I have 2 pounds, I have 2 cakes. Then you can figure out how much, how many of these things react and so forth and so on. So let's take a look at a second one. So the second one in this section is very similar. The only thing that's different here is they're going to add in the masses. So you have to do this in terms of mass. So this is, again, section 3.6. This is the second type of problem they want you to do. And all this is the same problem we just did, just we're adding in masses. So we have to do a couple of extra steps, okay? So the one that I'm looking at says that you've got green plants. They're using the light from a sun to drive photosynthesis. So then they tell you what the reaction is. They tell you that under photosynthesis, water reacts with carbon dioxide. It's actually the opposite of combustion. That reaction is going to give you glucose, C6H12. Now they give you the formula for glucose, and oxygen. They tell you it's O2. But remember from the previous lecture that if it's an element all by itself, there are 7 diatomic elements. So if they didn't even tell you it's O2, they just said it's oxygen, you could still know that it's O2, right? Because the diatomics were these. Okay, those were all the diatomics. But they, in this particular problem, they decided to tell you, okay? So now here's what happens. They tell you that in this reaction, you react 8.98 grams of water. So that's the number of grams of water that's reacting, that's given. And then they ask you to determine the mass of oxygen. Okay? Now, when you see a problem like this, you might ask yourself, well, they tell you the mass, but they don't tell you what the units are. So here's a good tip. If they give the mass in grams for the given material, then assume the answer is also in grams, right? It should be the same. So it should be some number of grams. If this was in kilograms, if water was in kilograms, then you would probably find the mass of oxygen in kilograms, okay? In general, when you do this type of problem, since they're both mass, so mass and mass, usually the numbers are not that far off from each other. So if it was 9 grams of water, you're probably going to get, you know, it's not going to be 1,000,000 grams of oxygen because, you know, conservation of mass. If you're taking 9 grams of something, you're not going to get 1,000,000 grams of something else. That would be creating matter. Likewise, if you're starting with 9 grams of water, you're not going to get 0.1 grams of oxygen. It's going to be somewhere in the range. You know, it might be as little as 4 grams, half as much. It might be twice as much. So it might be 18 grams, you know, but you're not going to get a big number. You're not going to get 10 to the 4th or 10 to the minus 4th. So 9 grams, you know, I'm not sure what it's going to be. My guess would be it's probably about 9, 18, it's probably like 16 grams or something like that, but we'll see. We'll go through it. Let's try it. Okay. So first step, just like we did in the previous problem, it's got to be balanced, right? So how do you start on this? Well, same thing. This thing right here, you're going to do last. The oxygen's all by itself. You do that one last. So what are the other elements? Carbon and hydrogen. Those are the only other 2 elements. So you could do hydrogen first and then do carbon. Or you could do carbon first and then hydrogen. It really doesn't matter. The key, though, is you do oxygen last because it's all by itself. So let's try it this way. See how there's more hydrogens over here than there are over here? That means we got to multiply this by some number, right? So n times 2 has got to equal 12, right? Now, technically, there's a 1 there, so it's really 1 times 12, right? It's really 12 times 1. But again, they're not going to put a 1 there, right? It's just going to say C6H12O6. So if you do the arithmetic, what you get is n equals 12 over 2, which is 6. So that means this is a 6 over here. So that's the hydrogen. Next one, again, don't do oxygen, do the carbon because we want to save the oxygen for last. So you do your carbon. So there's, you know, 1 over here, there's 6 over there. So there's more over here. So that means we're going to multiply this by some number. So n times 1, right? That's a 1. Again, not explicitly shown, but it is a 1, is equal to 1 times 6. Okay. All right, well, that's pretty simple. N times 1 equals 1 times 6. That means n times 1 equals 6, which means that n equals 6. So that means that's a 6 there. This one turns out to be a kind of a cool, when you do glucose, it's a kind of a cool balanced equation. So you got 2 6s there. So now we just have oxygen to do. Be careful with the oxygen because oxygen is in every substance in the reaction. It's in water, it's in carbon dioxide, it's in glucose, and it's in oxygen. It's in all of them. So that means it's a little more complicated. Count them all up. 6 oxygens over here, right? 6.
Wow.
6 times 2. So that's the left side. Let's do the product side, the right side. 6 over here. And then this one's going to be n times 2, right? Now, why did I put n times 2 over there? Because we want the left side equal to the right side, and we haven't put any numbers there yet. It could be they're the same, right? You might actually get the same with n just being 1, but let's figure that out. 6 plus 12 is 18, is equal to 6 plus 2n. Subtract 6 from both sides, and you get 2n. 12 equals 2n. Divide by 2, and you get n, and it looks like it's a 6. Isn't that cool? So now it's balanced. We've balanced the carbon, the hydrogen, and the oxygen. Everything is balanced in this equation, okay? All right, so once you've got it balanced, your next step, remember, that's exactly what we did in the previous problem. We just balanced the chemical equation. The difference here is that these are not moles. If it was, if this was 8.98 moles, if that was the given information, to find the moles of oxygen, we would just multiply it by the ratio 6 to 6, right? That would be very simple. But it's in grams. And like I said, if you don't know how much the cake weighs, you don't know how many cakes you have. If I say, hey, I've got 5 pounds of cakes, you have no idea how many cakes you have. So we have to do that here. We have to figure out how many moles of water we have. Mole is the counting unit you're going to use. If you were doing eggs, you would use dozens. But if you're doing chemicals, you're going to use moles. So here's how we go about it. To get to moles, we're going to do exactly what we did earlier in the week. It's a mass to mole conversions. And what we said was to convert from mass to moles, you divide by the molar mass. That is going to give you the moles of water, okay? That conversion, mass to moles, and the reverse, moles to mass, is probably the most standard calculation that any chemist does, or anybody taking a chemistry class, that's for sure. So you got to get really good at that. You divide by the molar mass to get moles. You multiply the moles by the molar mass to get the mass, okay? So what is the molar mass of water? Well, that's pretty easy. The molar mass of water, there's 2 hydrogens, so 2 times 1.01 grams per mole. The units of molar mass are grams per mole. And then there's only 1 oxygen. So that's 18.02 grams per mole. Okay. Now, if I used 1.00794 and 15.9994 for oxygen, you'd get a slightly different number. It might come out to 18.016 or something like that, but I'm just going to use what many periodic tables use. So there's your molar mass. Divide by the molar mass. Now remember, when we divide by the molar mass, we prefer to use dimensional analysis. So what you do is you're going from grams to moles, so you put the 18.02 grams at the bottom, and you put, oh my goodness, you put the 1 mole on the top. Okay. So 8.98 divided by 18.02, and you get 0.4983 moles of water. Okay. Now, that sounds about right. 9 divided by 18 is almost a half. It's about 0.5. So we got the right answer there. Now, you want to find the moles of oxygen. So this is just like the previous problem. So when I do this one, I'm doing exactly the same step I did before in the previous problem with the octane, the C8H18. What you do is you take the moles of the substance you're given, so that's right here, and you multiply it by the ratio. We call it the molar ratio. You'll see that term. It's the coefficient ratio. So you take the given number and you multiply it by the coefficient here. So 6 moles of oxygen divided by 6 moles of water. The one that you want divided by the one that you have. That way the moles of water cancel, and look what you get. The ratio is really 1. So that means in photosynthesis, for every 6 moles of water that you put in, you get 6 moles of oxygen out. So it's actually the same moles of water to the same moles of oxygen because of the balanced equation. Now the glucose is very different, right? The glucose, you only get 1 mole. So you have to put in 6 moles of water to get 1 mole of glucose out, right? So that's a very different ratio. It's a lot of, it takes a lot to get 1 mole of glucose, right? You need 6 moles of water, 6 moles of, that's a lot to get 1 mole of glucose out, okay? Now, the question is, how many grams of oxygen is that? So now it's the same idea as we just did here. Remember earlier in the week, like I said, if you want to go from mass to moles, you divide by the molar mass. But if you want to go the other way, if you want to go from moles to mass, you multiply by the molar mass. So that's all you got to do. You just got to multiply by the molar mass. So 0.4983 moles of O2 times the molar. Now, what's the molar mass of O2? Well, it's O2. So it's 2 times 16.00 grams per mole. So that's 32. Kind of cool. So times 32 grams of oxygen per 1 mole of O2. So you're just going to take the 0.4983 and multiply it by 32. And you get, boy, it's so close to 16. I'm going to round it to 3 sig figs, so it's 15.9. Now, why did I round it to 3? Because the given number only had 3. So I'm going to round it to 3. Okay. Take a look. Like I said, you start off with 9, and I think I said you get like around 16 or something like that. That's how it worked out. You got 15.9, so you got almost 16. So in that particular problem, I did really, actually, how many steps did I do? I guess I did 4. 1 was balancing the equation. 2 was taking the grams of water and converting it to moles of water by dividing by the molar mass. 3 was using this molar ratio, how many moles of this for how many moles of that using the balanced equation, step 3. And then step 4 was going from moles of the desired material, multiplying by the molar mass to get the number of grams of the oxygen. So 1, you got to balance the equation. 2, you got to convert the moles of the given. I'm sorry, not moles of the given. The mass of the given. Now that was in grams. Typically they're in grams, but they could be in micrograms. And if it's in micrograms, you convert it to grams. So mass of the given, 2 moles of given. Okay. Step 3, use the balanced equation. Use the coefficients in the balanced equations. To find the moles of the desired material. Right? In this case, it was oxygen. But, they could give you anything. They could say, look, here's how many moles of CO2 are produced. I'm sorry, here's how many moles of CO2 react. How many moles of glucose you're going to get. So in that case, the given would be the CO2 and the desired would be the glucose. You can do any ratio one to the other. And then step 4, convert the moles of the desired material to the mass of desired material. And of course, that conversion, mass to moles, you divide by the molar mass. And then to go from moles to mass, you multiply by the molar mass. Okay, and there you go. There's your procedure right there. That right step by step. That's going to work for 90% of these types of problems. It really, that's a very standard type of problem, and this will work for it. Okay, and if you go back and if you rewatch the video of how I did that, that problem that I just did with the glucose, you'll see that's essentially what I did. I balanced it. I converted mass to moles of the given material, which was the water. I then used the balanced equation, the coefficients in the balanced equation, to find the moles of the oxygen. And then I converted the number of moles of oxygen into the number of grams of oxygen by using the molar mass. So that little chart here at the bottom, you use it twice. You did it once to get to moles, and then you do it once to get to grams. Okay. Again, we can't really count moles. We can't measure the moles. There are some experiments that will allow you to estimate the number of moles, but they're not real precise for the most part. So what do? We measure mass, which we can measure very well, and then use the molar mass to convert it to moles to do our calculations, and then convert it back to grams. And then you can kind of, in section 7, there's a little problem where you actually see how close you are to the actual value. It's called percent yield. So those are the two types of problems in section 6, using the chemical equation for moles and then using the chemical equation for grams for mass. Okay. Now let's take a look at limiting reactant problems. So this is section 3.7. There's 3 types of problems that you want to do here. And the last one's actually pretty easy. It's theoretical yield. So what I'm going to do is I'm going to talk about the theoretical yield here, and then we'll move on to those 3. Okay. Let me just let me write it down first. Okay, so in the first one, you're doing mole to mole limiting reagents. Moles to moles limiting. They actually call it limiting reactant. Your textbook calls it limiting reactants. Okay, so in this one, they say that solid phosphorus, so they tell you phosphorus is P. Now, usually phosphorus is P4, but for them, they said just make it P, so that simplifies things. And chlorine, and they tell you it's Cl2. Remember, Cl2, chlorine is a diatomic. So they tell you these are going to react to form phosphorus pentafluoride, and they give you the formula. Okay, so here's your reaction. They give you this reaction. They tell you that's what it is. And then they give you the states of matter. They say the phosphorus is solid. They say the chlorine is a gas. And then the phosphorus pentafluoride is a solid. So they're giving you the states of matter. Okay. And then it says, suppose you have 13.0 moles of phosphorus and you have 11.0 moles of chlorine. How many moles? Actually, let me be careful here. What would be the limiting reactant? Actually, they're just asking you, what is the limiting reactant? Okay, so they just want you to write the chemical formula. Okay, so in this particular problem, it's very limited what you have to do. But what I'm going to do is I'm going to do the following. I'm going to show you the procedure here for figuring this out. Now, there's a couple different ways that people do this. I'm going to show you the way that will help you actually do more advanced problems. Essentially, what we've got here is an equation that's not balanced, right? So whenever you do reactions and you're doing calculations with them, you do want to balance the equations. So we do have to go through that step first. What's different about the limiting reactant problem compared to the one we just did, 3.6, is we're given the amounts of both reactants, not just one of them. So we now have to take both of them into account. And it may not be intuitive to see how that works, but I'll show you the whole idea. Essentially, what you do is you figure out how many moles of the product you could get from each of the reactants separately. And you're going to get two answers, right? You'll figure out how much PCl5 you could get from the first reactant, phosphorus, P, and then how much you could get from the second reactant, Cl2. Pick the smaller of the two. Okay, that's all you do. Okay. So let's start with the balancing. We've got one phosphorus over here. We've got one over there. That's good. How many chlorines do we have? We have 2 on the left and 5 on the right. Now that's a little tricky, right? How do you deal with that? Well, what I'm going to do is I'm going to say, what's a common denominator of 2 and 5? Well, one common product would be 2 times 5, right? If you just took 2 times 5, you get 10. And so 2 goes into 10 evenly, so does 5. So let's just multiply this one by 5. So 5 times 2 is 10. And let's multiply this one by 2. 2 times 5 is 10. So now the chlorines are balanced. But notice that's unbalanced the phosphorus, right? Because now we have 2 on the right and only 1 on the left. But that's very easily resolved. Just put a 2 over there. Right? So now you have 2 on both sides. So, this one is a little different than the combustion because there's 2 reactants in one product, but it's a relatively simple one. You can play around with this one and get it. Okay, so step 1, balance. Right, that's the first step. Step 2, calculate moles of the desired. Now, I don't say product here, I say desired because they might tell you how many moles of the product you got and you have to find the moles of the reactant. So you never know which one they're going to tell you. But in this case, it was the desired one is the PCl5. In fact, in this problem, they don't even ask you for the amount. But what I would do is I would say, okay, they gave you the moles of this one. They gave you the moles of this one. What's the thing we can calculate? This one. So that's the desired one. Okay, actually, they didn't even tell you that's the desired one, but I'm showing you a method for doing this. So calculate moles of desired from each reactant separately. Do it separately, 2 separate calculations using the balanced equation. So let's try the first one. First one, we have 13 moles of P. Moles of PCl5. So it's 2 moles of PCl5 for every 2 moles of P. Well, you get 13 moles. Okay, so I did it from the first one. Now I'm going to do it from the second one separately. What I mean is a separate calculation. How many moles of this? How many moles of that? 11 times 2 divided by 5. Now what you get here is 11 times 2/5. So that's 11 times 0.4. So that's 11 times 0.4, which is 4.4. So now you have 2 answers. And the question is, which one's right? Maybe they're both right. Maybe they're both wrong. Who knows? What do you do? Think of it this way. The amount of finished product that you can make in a factory depends on every ingredient that you put into the factory, right? So like if you're trying to build a car and you have no tires, you can't make the car. The car needs tires. So if there's no tires, you can't make a car. If there's no engines, you can't make a car. If there's no steel, you can't make the car. If there's no plastic, right? So making a car requires everything that goes into making a car. So the question is, what happens if you run out of one of the ingredients first, one of the items that you need to build it? That would be called the limiting reactant. The limiting reactant is the substance that runs out before you have used up everything else. So if I am making sandwiches with bread and cheese and I have no cheese, the cheese is the limiting reactant. if I'm making sandwiches and I have a lot of cheese, but I have no bread, the bread is the limiting reactant, okay? The material that you don't run out of is called the excess reactant. So there's two types of reactants. There's the limiting reactant. By the way, the limiting reactant is typically the more expensive material. You run out of the more expensive material. So if you're doing a reaction with gold and chlorine, you're more likely to run out of the gold. So the gold will be the limiting reactant. And then you got the excess reactant. That's a C. And then when you Google this stuff, sometimes you'll see the word reagent. Reagent is the same as reactant, means the same thing, okay? Or effectively the same thing. So in this problem, they're asking us to identify what would be the limiting reactant. Just enter its chemical formula. The limiting reactant is the reactant that produces less of the product than the excess reactant, the one that gives you the smaller amount, okay? If you get the same answer for both, let's say you got 6.5 moles of PCl for 5, that would mean there is no limiting reactant and that the reactants are stoichiometrically matched to give the same amount of product. Most likely you're not going to see that in these problems. And one of them is going to be the limiting. So the limiting is the one that gives you the smaller amount. So which one gave us the smaller amount? Well, first of all, the smaller amount is the 4.4. That's smaller than 13. Which reactant gave us that smaller amount? Cl2. So that would mean that the chlorine is the limiting reactant. Okay. If it had been that for the phosphorus, we started off with 1.3 moles of phosphorus. So like if this was 1.3, then that would give us 1.3 moles of PCl5. And now the phosphorus would be the limiting reactant. Okay, so again, the limiting reactant is the reactant that gives you the smaller number. It limits how much of the product you can get. So think of it this way, you're flowing in chlorine gas, you're putting in phosphorus, they're reacting together, and they're combining to give you PCl5 out. For those of you that are computer science majors or math majors, you can think of it sort of like a function, right? You put a variable x in and you get an f of x out. It's essentially what a chemical reaction is. The reaction, the amount of product you get out is a function of how much chlorine you put in, how much phosphorus you put in. What we've determined is that the phosphorus is the limiting reactant. It's the limiting variable. It limits how much of the PCl5 you can get out. There's only enough to make 4.4 moles of the PCl5. In order to get more PCl5, we don't need to add more phosphorus. We need to add more chlorine. The chlorine is the limiting reactant. I'm sorry, I might have said phosphorus is the limiting reactant, but chlorine is the limiting reactant. So if you want to get more PCl5 out, you got to put in more chlorine. You don't need to put in more phosphorus, right? The phosphorus is in plentiful. There's enough to make 13 moles of PCl5. So if we scale up the chlorine, we'll get more PCl5 out. Okay. Let me show you one more. So in this one, that's the same reaction. So sometimes they have you do the same reaction. I want to look at a different reaction. Here's one. Okay, this one, they actually want you to do a calculation. So the wording sometimes are differently in here. So read these carefully. It's not the same each time. So in this one, they tell you they have solid aluminum and it's reacting with chlorine gas. Notice how I'm putting a little room between these, so if we need to balance it. And they're going to produce solid aluminum chloride. They give you the formula. Okay. And then they say, suppose you've got 7.0 moles of aluminum and you've got 1.0 moles of chlorine. Calculate the largest amount of aluminum chloride. Now, how do I know it's moles and not grams? They actually tell you, round it to the nearest 0.10 of a mole. So that's moles, okay? Now, this is a different question. It's not asking us which the limiting reactant, but we will determine that, okay? So step one, balance the equation. Aluminum is already balanced, so that's good. But what about the chlorine? There's 2 chlorines on the left and 3 on the right. So again, if those numbers are not equal, what you can do is you say, well, what's 2 times 3? Is 6. So 3 times 2 is 6, and 2 times 3 is 6. Now the aluminum needs to be fixed by putting a 2 over there. That's kind of fun, right? So there you go. There's your balanced equation. Okay. Now, same thing. Figure out how many moles of aluminum chloride you're going to get from each reactant. So 7 moles of aluminum. And it's 2 moles for every 2 moles. So times 2 moles. And you get 7 moles, right? So it's kind of like the other one with the phosphorus. You get the same amount, right? So sometimes the coefficient's a 1, or sometimes the coefficient is not a 1, but the coefficients are the same, 2 to 2. So 2 over 2 is 1. So it ends up being the same, right? So, okay, what about the other reactant? We got the chlorine. So we're given that it's 1 mole. So you're taking the amount that's given and multiplying. Let me write down that's chlorine, sorry. And you're multiplying that by 2 for every 3. Right, the one you want over the one you have. So what is that? 0.67. Okay, so first of all, it doesn't ask us, but let's identify the limiting reactant. The limiting reactant is the one that gives you the less of the product, the smaller amount. So the less product is this one right here. That's the smallest amount, the smaller amount. So it came from chlorine. So chlorine is the limiting reactant. Okay. Is chlorine more expensive than aluminum? It's a good question. I'm not sure. Aluminum can be recycled. Chlorine's hard to recycle. So it could be chlorine's more expensive. Or it could be that they just didn't take that into consideration here. So the limiting reactant is chlorine. But the other reactant would be the excess. So the excess reactant, that's the one that we could give you more. You have enough to get more. So that would be the aluminum. Okay. And then the product is the AlCl3. We wouldn't say there's a limiting product or a excess product. There's just a product. Okay. So now the amount you can actually get is given by the limiting reactant. So the limiting reactant was chlorine. It gave you this amount. That's the max you can get out. So your answer would be 0.67, although they said rounded to the nearest 0.10. So that would be 0.7. So that's how much you could get. That is essentially the wording they use is a little tricky. The largest amount that could be produced. The largest amount that can be produced is the amount you get from the limiting reactant. Okay. There's just not enough chlorine to make any more than 0.7 moles. There's only enough to make 0.7. So that would be the maximum amount you could get. This is the maximum. Now you could actually get less, right? So if you've ever baked a cake, you know there's always a little bit of batter at the bottom. You lose some of it, right? And some of it's stuck to the measuring cup. So you're not actually getting the same amount of cake that you measured in when you did it. Same thing here. We might lose some of this AlCl3 somehow, but that's the maximum amount you could get. Okay. So that is the second type. The third type, let me just make sure. Oh, actually, I'm sorry. That's actually the first type. So the second type, there was just 2 versions of the first type. The second type is a little bit more complicated. Here, they're going to give you masses and you have to figure out moles, okay? So this one is just, they just entitled it Limiting Reactants. Reactants, okay? So in this one, the wording is more complicated, but it's the same idea. aqueous hydrochloric acid. They give you the chemical formula. Remember, aqueous is AQ. Will react with solid sodium hydroxide to produce. So to produce means you write the arrow. Aqueous sodium chloride. So they give you the formula, CaCl. Aqueous is AQ. And liquid water. So H2OL. Okay, so there's your balanced equation. This one's already balanced, so don't worry about balancing it. You know, this one is fine, right? If you count up, there's 2 hydrogens on both sides. There's 1 chlorine on both sides, 1 sodium on both sides, and 1 oxygen. So sometimes they're balanced, right? Acid-based ones are often balanced. Suppose 32 grams of hydrochloric acid. So 32 grams decimal mixed with 48.8 48.8 grams. And then in this one, they want you to find the maximum mass of sodium chloride. Right. So notice how earlier I said if you're given grams, you're going to want to figure out grams. Same thing here. There's no difference with that. Okay. So how do we go about this? This is just like the one we did. It's just that we have to convert grams to moles and moles to grams, that kind of thing. So it is going to be a lot of steps, though. So same idea, though. 1, balance. It's already balanced. 2, convert to moles. Okay, so step 2, convert to moles. So I'm going to do this kind of quickly based on my memory, but you know that's just to save time here. We've got 32 grams of HCl. Divide by the molar mass to get moles. So 1 mole of HCl is 36.46 grams of HCl. That's the molar mass. Remember, you divide by the molar mass to get the number of moles. So 32 divided by 36.46, and you get 0.8776. I'm going to put a lot of sig figs there. Okay. Step 3, use the balanced equation. So you use the equation to find moles of the product or moles of the desired material. Okay. Well, the desired material here is sodium chloride, NaCl. That's the one they're asking for. So let's do that. 0.87767. We'll round it at the end. The ratio is 1 of these for every one of those. So times 1 mole NaCl for every 1 mole HCl. Okay. So you're going to get 0.877. Same number, right? Don't forget that step, though, because if the balanced equation has 1s and 2s and 3s, you know, the coefficients aren't all the same. You won't get the same number. So then step 4, convert to grams. Okay, remember to convert to grams, you multiply by the molar mass. Now we're dealing with NaCl. So 0.87767 moles of NaCl. How much does NaCl weigh? It's 58.44. I just calculated that in my head just to save time, but you can check that, right? Check through it. Sodium and chlorine, you'll get 58.44. So 0.87767 times 58.44, and you get 51.29 grams of NaCl. Okay, so notice what I did. That's just like the 3.6 problem where you took the grams of the reactant and you found the grams of the product. But this is a limiting reactant problem. So how is this different? The way it's different is that we're given the amount of 2 materials. So you do exactly the same calculation with the second reactant. So you do step 2, 3, 4, find the grams of NaCl. Why? Because we want to know what the maximum amount of NaCl is. To find the maximum amount of NaCl, we have to figure out which one of the reactants is limiting and then figure out the smaller of the 2. So I'm just going to go through and do step 2, 3, 4 again, but using the NaOH. Okay. So 48.8 grams of NaOH. And then how do you convert it? Well, you divide by the molar mass. What's the molar mass of sodium hydroxide? Sodium, oxygen, hydrogen. It actually works out to be 40 exactly. Well, at least with 4 sig figs. Okay, so 48.8 divided by 40, and you get 1.22. Step 3, use the equation to find the moles of the desired material. That's this right here. So 1.22 moles NaOH. And then we already figured out we already figured out it's 1 to 1, right? It's 1 to 1. So 1 mole of NaCl for every 1 mole NaOH. So again, you get 1.22 moles of NaCl. And then last step, convert moles to grams using the molar mass. So 1.22 moles of NaCl times, how much does it weigh? It weighs 58.44. We already have that number up here. Grams of NaCl for every mole. So 1.22 times 58.44, and you get 71.2968. Okay, now you got 2 answers. So I'm going to circle both those answers. Pick the smaller of the 2, right? When we did the previous problem, limiting reactances, you're given the reactant, the amount of both reactants, or all 3, or all 4. You figure out how many grams or moles of the product you can get from each of them. Pick the smallest of them. So the smallest one is this one right here. This is smaller. So our maximum is 51.79. They're going to tell you to round it to 2 sig figs. So 2 sig figs would be 52. So our answer is 52 grams. There's your maximum. 71.29 doesn't work because even though we have enough NaOH to get 71 grams of NaCl, we don't have enough of the HCl. There's only enough HCl to get 52 grams. So that's our answer. You pick the smaller, round it to 2 sig figs. Then you say, which one's the limiting? The limiting is the one that gave you the smaller amount. So backtracking. It doesn't ask you for this. It just says how much you're going to get. But if you look at it, the HCl is the one that gave you 51.79 grams. That's where we got that number. So that's the limiting reactant. The actual amount you're going to get, well, I'm not going to call it actual. Let's be careful with terms. The maximum you could get is 52 grams. We wouldn't say the actual. Actual means something different in this context. So we'll call it maximum. So actually, Alex does a good job. When they program that one, that's good. They could say the maximum you can get. The excess reactant is here. That's the one that gave you more. Okay. All right. So that is essentially the limiting reactant topic. It's a kind of intense topic. So you may need to watch the videos more than once, and you may need to find other videos that I've posted as well. It's not the simplest idea. It's a lot of steps, but the whole basis of it, again, is this idea that really what you're doing is you're saying, look, you got more than one reactant. So they got to go in to do the reaction, and then you get your output, which is the product. So reactant 1, reactant 2, this is your reaction. We're not talking about the reaction itself. That's a whole fascinating aspect of chemistry. That's really, in the end, one of the things that drives us in terms of understanding is how is this reaction occurring? We're going to talk about that later. That's in a subsequent chapter. But for right now, we're just calculating how much. And so what we've done is you have an input, reactant 1, an input, reactant 2. They're combining according to certain ratios, and then that's going to give you the maximum amount that you can get out. Okay. So the last one in this section is, because I didn't put a whole lot of them in here, I only put a couple, is theoretical yield. So let's talk about theoretical yield. Okay, so theoretical yield is equal to the maximum amount. So that's what we just calculated, right? In that previous problem, what was the maximum amount? That's the theoretical yield. Okay, so that's what we're talking. Now, there's something called the actual yield. The actual yield is the amount you actually the amount that you measure in the lab. So this is the amount that you measure in the laboratory. That's the actual amount. So theoretical is not the actual amount, it's what you calculate, right? A calculation is not an actual, a calculation is a theory, right? That's how much we think you would get. The actual yield is what you actually measure in the laboratory, okay? So they don't necessarily have to be the same. So what happens is we do this little calculation called reaction yield. And the reaction yield is the actual yield divided by the theoretical yield times 100. That's called the reaction yield. So suppose I do a problem. Let's say it's, N2 plus 3H2 to give 2NH3. And what I do is I put in a certain amount of these. So I'll call it mass 1 and mass 2. And I do the calculation that we just did. I calculate it out. And what it turns out is we get, 2.5 grams of ammonia produced. So this is called the theoretical yield. So this is something you would calculate from the balanced equation, right? Then I go into the lab and I use a balance. And what I get is 2.25 grams. Okay, see how it's smaller? Just like I said earlier, if you're cooking something, some of the stuff will stick to the pan, some of it'll get thrown out as you're mixing it, so you lose some of the material. So you get less experimentally than you calculate you would, right? So we call that the actual yield. Pretty simple. So then, as a measure of efficiency, how efficient were we in our procedure? Did we get all of what we expected? Well, that would be 100%. Did we get none of what we expected? That would be 0%. In practice, it's going to be somewhere between 0 and 100. So what you do to calculate the efficiency, we'll call it efficiency. Now, efficiency, you have to be careful with that word because engineers have specific meanings for what efficiency is. But in a sense, that's what we mean here by reaction yield. How efficient were you? Right? How close to 100% were you? The way you calculate it is you take your actual yield, 2.25 grams. You divide that by your theoretical yield, which is 2.5 grams, and then you multiply it by 100%. So, what is that? 4/8, that's 9/10. So it's 90%. Okay. And so 90%, that's pretty close, right? Now, is 90% good or bad? It depends on the experiment. Some experiments we might demand 95% in order to be good. Other experiments might be very complicated and you're lucky to get 30%, right? So chemists will spend time trying to increase these percentages. They don't want to get 30%, they want to get 60%, but sometimes they're limited. The reactions could be complicated and it may not be easy to get it above 30%. So it just depends on the case. For a reaction like this, it's very simple, N2 plus H2. You should definitely get over 90%. That's a really simple reaction. We should be able to get 95% out of that. They make ammonia in factories by large amounts. I'm sure they're trying to get 90, 95% they might be trying to get 98% actually. Okay, so hard to say. But in any case, those are the three terms. Theoretical is the maximum amount. That's what you calculate, just based on the numbers. Actual yield is what you measure in the laboratory. So you take your product and you put it into a balance and you measure it. That's the actual yield. The reaction yield is the efficiency. So you take the actual yield, what you actually get, divided by your theoretical yield, what you calculate, take a ratio, multiply by 100 to convert it to a percent. And typically these are in either grams or moles. Typically these are grams or moles. And then if they have to be the same though. You want these both to be grams or both to be moles. You don't want to mix that. Because when you take the ratio, if they're in the same units, you get rid of the units, right? They cancel. So grams over grams, moles over moles will get rid of the units. And then you multiply it by 100 to convert it to a percent. Okay? So for this problem, what they want you to do is to calculate the theoretical yield. So you're doing the calculation here. That's this right here. That's what we just did previously in the previous problem. So this one, even though it may sound different, it's actually the same problem we just did. So this is going to give you another example. So it says here gaseous butane, and they give you the chemical formula. Now I'm going to show you the way they give it to you. They do it as CH3, CH2, CH3. They say it reacts with oxygen gas, so O2G, and then it forms gaseous carbon dioxide plus gaseous water. Now here's the issue. Well, let me just go through the whole question. What is the theoretical yield of water produced from, so what's the theoretical yield of the water when you react 27.3 grams of this is called butane, and 130 grams of oxygen. So notice there's a lot, oops, I wrote it in the wrong place. There's a lot more oxygen here. Most likely the oxygen's the excess reactant. Here's the problem with this. The way that they've written this, it's going to be tricky to balance it. So let's condense this down. They're just trying to show you what the structure of this molecule is by writing it as CH3, CH2, CH3. What we're going to do is we're going to condense it. Condensing is count up the number of carbons you have. 1, 2, 3, 4. So it's a total of 4. 3, 2 times 2 is 4, 3. So that's 10. Now you can balance it more easily. We don't need to have that structural formula. We can use the condensed formula. Okay, now you've got your 27.3 grams and you've got your 130 grams. It's going to be easier to do this. Theoretical yield. Theoretical yield, just like we did in the previous problem. What's the maximum amount of product you're going to get for the water? So how many grams? So it's got to be balanced. I'm going to do the balancing quickly. There's 4 carbons here, so I'm going to put a 4 there. There's 10 hydrogens there, so I'm going to put a 5 there. 5 times 2 is 10. Now we do the oxygen. We're going to have an odd number. 4 times 2 is 8. 5 times 1 is 5. 8 plus 5 is 13. Over here we have 2. So again, just like we did before, you put an n there. N times 2 equals 13. Divide both sides by 2, n equals 13 halves. Now, for this one, am not going to multiply everything by 2. I'm just going to leave it as 13 halves, and you'll get exactly the same answer. So if you multiply everything by 2, you'll get the right answer. I'm not going to do it. It's going to make the problem look a little weirder because we're going to have a fraction in it, but you'll get the same answer because all you need are the ratios. So again, same idea. Figure out how many moles you have, use the molar ratio to get the moles of the desired product, use the molar mass to convert it to grams. Do it for both. Pick the smaller number. That's your theoretical yield. Okay, so let's do it with the first reactant. 27.3. Now, if this was already in moles, we wouldn't have to do this step. So how much does C4H10 weigh? Was that 48? 58.14. That's the molar mass. So 27.3 over 58.14. It's a lot like sodium chloride, 58.44, but this is 58.14. 0.4696 moles of C4H10. Use the balanced equation. We're interested in water. Oh, so make sure I don't use this up here. We're going to use the balanced equation. It's 5 moles, right? So 0.4696 moles C4H10 it's 5 moles of this for every 1 mole. So 5 moles of H2O for every 1 mole of C4H10. Okay. If you'd multiplied everything by 2, you would have 10 and 2. 10 over 2 is the same as 5 over 1. That's why you actually don't need to get rid of the fraction. It gives you the same answer. So you get 2.348 moles of water. Okay, now we convert that to grams. 2.348 moles of water times 18.02. Remember, multiply to get the grams. You multiply by molar mass to get grams. You divide by molar mass to get moles. So this times 18.02, and you get 42.3. I'm going to round it to 3 sig figs, which is what they ask you. Now that could be the answer. That could be the theoretical yield. That could be the maximum amount. If the butane is the limiting reactant. So if that's the limiting reactant, the C4H10, then that would be the answer. But we don't know whether it is. Maybe the oxygen is the limiting reactant. So how do you tell? Oxygen's cheaper than butane because it's in the atmosphere. It's produced by all the plant life on the earth. So it's probably not the limiting reactant. The more expensive material is the limiting reactant. So butane probably is, but that doesn't mean that that's the way they wrote it. That would just in general be the case. We have to be careful. So let's try the oxygen. Now there's a lot of oxygen, 130 grams, but don't be fooled. Just because the mass here is greater, that doesn't mean it's the limiting reactant, because there's a couple things that go into it. How much it weighs, the molar mass, and then what the molar ratios are. That can vary. So if you look at these molar ratios, see how this 13 halves to 5 is not the same as 1 to 5. So be careful. So now do the same thing for the second reactant, O2. 130 grams. Okay, how many moles is that? Well, 1 mole of O2 is 32 grams. Divide by the molar mass. Where did I get 32? You look it up in the periodic table. 16 times 2. O2 is 16. I'm sorry, O is 16. O2 is 16 times 2. 16.00 times 2. But again, if you're doing it on Alex, use their values in the periodic table. 15.9994 times 2. And that'll give you 31.9996 or something like that. So 130 divided by 32. It's about 4 moles. Then you look for the material you want, 5 moles of this over 13 halves. So 40625. And then it's 5 moles of water for every 13. Now what's 13 over half? 13 over 2. 13 halves is 6.5. So 6.5 moles of O2. Makes it a little easier to write. So 4.0625 times 5 over 6.5. And you get 3.125 moles of water. Now that's going to work out to be around 60 grams. So it's probably going to be bigger, right? The issue is which one's smaller. You want the smaller numbers. So probably that one's smaller, 42.3. But let's just check. 3.125 moles of water. Water weighs 18.02 grams. So I think that's going to be more than 42.3. 3.125 times 18.02, and you get 56.3. I already rounded it to 3 sig figs. It is bigger, right? That's bigger. We want the smaller amount. That's the maximum. The maximum is the smaller. The theoretical yield is the smaller. So maximum theoretical yield is the same. So our answer then is 42.3. So 42.3 grams is the max amount. This number is really not that useful. We can't even really use that number for anything. It just says that we could make 56.3 if we added more butane, right? We have enough oxygen to make 56.3, okay? So our answer is 42.3. That would be called the theoretical yield, which is the maximum amount if we went back to the previous type problem. Okay, so theoretical yield, maximum amount, smaller amount of the two, right? And if we had 3 reactants, you would just do it for all 3 and figure out which one is the smallest of the 3. Okay, so in this one, it was consistent. They made the butane the limiting reactant. So this one's limiting. Think of one of those little disposable lighters, right? The Bic lighters with, the green or blue or red or yellow plastic container. You can see the butane in there. The butane is that liquid on the inside. But what happens is when you open the valve, you push down with your thumb, not the actual flint, but the just opening of the valve. When you open that, that's essentially allowing it to escape. And what happens is, butane's interesting. Its boiling point is a little bit below room temperature. Or, it's like 5 degrees C or something like that. So what happens is when you open the valve, the pressure on the outside is now less than the pressure on the inside. So it escapes as a gas. It essentially boils, is what it does. But if you allow the valve up, you close off by taking your thumb off, it closes it, and then it starts to boil, but now it's blocked, so it stays in there. The pressure builds up on the inside so that it stays in the liquid form. Then when you flick it with your thumb, right? You're doing 2 things with your thumb. You're pushing down on the valve to open it, but you're also turning that little thumb wheel, and that thumb wheel is a flint. It causes a spark. It's essentially just a metal on rock. It's actually 2 metals, most likely. So as it makes that spark, that ignites the gas that's coming up, right? So you may have seen those movies where someone goes into a gas station and you got the pump, right? So you get the pump there. And what they do is they pour some of the gas on the ground, and then they light a match, and that blows up the whole gas station. That is most likely not going to occur, because what happens is all that gasoline underground is in the liquid form. And it's liquid all the way to here. It's pressurized to be a liquid. There's really no gas there. So what happens is it's actually kind of difficult to get a liquid to explode because the exposed surface area is so small. So gases are more likely to explode because the molecules are spread out, so the oxygen can mix in with them and then burn everything at once. Explosion is essentially what happens when you get such a rapid burning that it moves so rapidly. It's faster than the speed of sound, and that's an explosion. So what would normally happen is it would burn. You might get a little poof out here until it got to there. And then most likely what would happen is this valve is closed off here. So it would just stop. So it's not likely to explode, right? But it looks cool in a movie if it does explode. Okay. So that is the last problem for limiting reactants. There's really only 3 of them that you have to do. Mole to mole limiting reactant, gram to gram limiting reactant, and then theoretical yield, which is really just gram to gram limiting reactant. So it's just those 3. So those 2 sections are 6 problems. 3.6 is 2 problems, and then 3.7 is 3 problems, and you're done. But those problems are difficult unless you really are very good at doing mole to mass, mass to mole, and balancing equations. So remember, go back to section 3. Watch the lecture on section 3 if you need more practice balancing equations. And then 3.4 is the mass to mole and mole to mass conversion. So that's in there as well, okay? And then that pretty much is it for chapter 3. So let me just take a couple of minutes here to mention a little bit about chapter 4. No, I didn't want to save that, but that's okay. Let me talk a little bit about chapter 4. Chapter 4 also, so this is reactions. Chapter 4, aqueous solution. Okay. Chapter 4 also has a lot of problems in it. Just looking at here, it's 15. Okay. So 15 is kind of up there. It's not as many as chapter 3, though. Okay. Now, I do have, it looks like at the end of chapter 4, you have to take a knowledge check, a progressive knowledge check. So once you finish chapter 4, save in a little bit of time for your uh, knowledge check. That'll come in at the end. Okay. So what we're going to cover in chapter 4 is really precipitation reactions, acid-base reactions, oxidation reduction reactions, and then finally we'll go back to calculations using moles and molarity. So we've got 4 different topics that you're going to cover in there. Okay. So let me, I'm just going to sort of end it right there. Let me just make a couple of announcements real quick. I will put this in an email on on Blackboard. But the first one is that if you're in section 11A, that means you're doing the remote labs, right? Okay. So that means that what you're going to have is you're going to have your lab reports are due on Sunday nights. So that means your reports are due Sunday nights. So that's coming up. So the first lab report for you guys is due this Sunday, and that's the calibration of volumetric glassware. So make sure you turn that in. The instructions for turning that in are in the syllabus, the laboratory syllabus. So open up the laboratory syllabus and look for that document. So you're going to have to, you have to watch the experiment, you have to read through the procedure, and then you have to do the report sheet. The report sheet has 4 questions. That's what you attach in your lab report. You don't have to go through all the calculations that the instructor does. You just have to turn in that lab report sheet. That's on Blackboard, and you're going to turn that in. You got to follow the formatting for it, and that's due Sunday. For those of you that are in B, you're the ones that are doing the on-site, right? You're coming in. You've already done your lab report. You're done with that. You did the density experiment on campus on Tuesday. So your report is done. Okay. So you're done for that lab report. Okay. So then that's due. 2, the first objective for chapter 3 is due Sunday night. All right, so that's due as well. So that's those 22 topics. Is it 22? Let me move this over. 22 topics for chapter 3. So those 22 topics are due. Now here's what happens, just to kind of help you out if you're going to panic. If you don't finish those 22 topics on time, let's say you finish half of them, 11, you'll get credit for the 11. You'll get 50% score. So it's not like a all or nothing. You can get percentage score for what you finish. Also, what you can do in the future is if you didn't finish, let's say you finished 18 out of 22, so there were 4 you didn't finish. It's not good you didn't finish them on time, but it doesn't completely kill you. When you finish a subsequent chapter, let's say you finish chapter 4 early, if you finish the next chapter early, it will reopen those 4 topics that you didn't finish, and you can turn them in and get, I will call it partial credit. You'll get around 40% of the credit, right? So if you do all 4 after that, you'll essentially get credit for half of it, something like that. So that would be like 20 out of 20. You won't get the full credit, but you'll get part of it. The way you get the partial credit is it goes into your pi. So the pi is part of your grade. So if you turn it in late, you can do it then. But you can only do that if you finish the next topic, the next chapter early, so you have time to do it, or the next chapter after that. So if, let's say, you don't have time after chapter 4, but you have to have time after chapter 6, it'll open up all the topics you didn't finish on time, and you can go back and do those. But you have to do them early, right? That next objective has to be done early. So that's due Sunday night. And also exam 1 is due Sunday night. Now you can take exam 1 now, but it's also due Sunday night. Okay, you only get to take that once. It's 10 questions on Alex. And there are practice exams. right? Practice exam 1 is available. You can practice that. I have it set up that you can practice it, I think, unlimited number of times. I think that's the way I set it up. There's some kind of limits in terms of how you can do it, but you can do the practice exam. The practice exam, you do not get extra credit for doing it. You do not get punished if you do not do it. It does not affect your grade in any scores. It's just practice. It is longer than the actual exam. It's quite a bit longer. It's like 20 questions or something like that. The actual exam is only 10, but that's just to give you more practice doing the problems, okay? So everything is due Sunday night. The only time that not everything is due Sunday night is at the end when the extra credit assignment and the last laboratory report, you'll have to kind of really crank that out at the end. The extra credit and the last lab, which is spectrophotometry, that gets done all the way at the end. For those of you that are doing remote learning, for those of you in section A, for those of you in section B, all the lab reports are done on campus. Okay, so you'll be done with that no matter what. All right. So 3 things to be aware of for Sunday night: the objective, the lab report, and then the exam. There are no makeup dates because you are given the whole week to take the exam. So it's expected that you'll work out your schedule to get the exams done. And then, like I said, lab reports the same thing. Lab reports, you had the whole week to do it. So you have to get that done on time. Okay. So this will be posted, and good luck this weekend getting everything all done. I'm taking a math class myself, so I've got an exam and a bunch of homeworks to do this weekend too. So I'll be busy myself.
Professor?
So enjoy and have a great weekend.
Professor?
And then we'll be back on Monday and we will start working on chapter 4.